So let's take a look at derivatives and integrals of vector functions. So let's say we have the vector function r of t, and that is equal to, in component form, f of t, comma g of t, comma h of t. And so this can also be written as f of t times I, the unit vector, plus g of t times j, plus h of t times k, in that unit vector form. So if we were to take the derivative of this vector function, it's going to be r prime of t. And so when we take the derivative, we take the derivative of each individual function. So f of t, g of t, and h of t. So in component form, it's going to look like f prime of t, g prime of t, and then comma h prime of t. And then in unit vector form, we can also write it as f prime of t times I plus g prime of t j, and then plus h prime of t times k. So for number one, let's go ahead and find the derivative of the vector function r of t equals t squared comma 1 minus t comma square root of t. So once again, when we're going to take the derivative of this specific vector function r of t, we're going to write it as r prime of t. And so when we take the derivative, we're going to take the derivative of each individual component function, so all three of these. So the first one, t squared, the derivative of t squared is just 2t. Now comma the derivative of 1 minus t, and so the derivative of 1 minus t is negative 1. And then the derivative of square root of t is 1 over 2 times the square root of t. So that is going to be the derivative of this vector function. So for number two, we have to find the derivative of r of t equals I minus j plus e to the 4t k. So once again, r prime of t, we're going to take the derivative of each individual component. So the first one is I, and the coefficient in front of I is just simply 1. So that is going to be that x component. And so the derivative of 1 is simply just 0. So we get 0i, and then now plus the coefficient in front of j is negative 1. And the derivative of negative 1 is simply 0, so we have 0j. And then we have plus, now the coefficient in front of k, or the function in front of k, is e to the 4t. And so the derivative of e to the 4t is going to be 4e to the 4t times k. And so the zeros will obviously cancel when they're multiplied with I and j. And so what we're left with is the derivative r prime of t is going to equal 4e to the 4t k. And in component form, it can also be written as 0, 0, 4e to the 4t. So for number three, we have r of t equals e to the t squared I minus j plus the natural log of 1 plus 3t times k. So now r prime of t, once again, the derivative is going to equal the derivative of e to the t squared, which is in front of I. So we're going to take the derivative of that, which is 2t e to the t squared times I. And now we have plus the derivative of the coefficient in front of j, which is simply just negative 1. Derivative of that is 0, so we just have 0j. And then plus the derivative of natural log of 1 plus 3t. Now the derivative of a natural log of 1 plus 3t is going to be the derivative of the inside function, which is simply just 3, over the inside function 1 plus 3t. So 3 over 1 plus 3t. k. So we can go ahead and eliminate that 0, because 0 times j is simply 0. So we're left with 2t times e to the t squared I plus 3 over 1 plus 3t times k. That is the derivative. So for number four, we have r of t equals a plus t times b plus t squared c. Now, because there's a, b, and c, it might look a little bit confusing, but treat these as the unit vectors similar to I, j, and k. So a would be associated with the x component, b would be with the y component, and c would be with the z component. So r prime of t, now the coefficient in front of a is simply just 1, and the derivative of 1 is 0, so we have 0 times a, and then plus, now t is the function in front of b, and the derivative of t is just simply 1, so we get 1 times b, which is b, and then plus, now the derivative of t squared is 2t, so we get 2t times c. So r prime of t, the final answer for the derivative of this specific vector function, is going to be b plus 2tc. Now moving on to the next set of questions, let's say we're trying to find the unit vector. So remember, if we're trying to find the unit vector for, let's say, vector named A, then the unit vector formula will be equal to the vector A over the magnitude of A. But now, instead of vector A, we're looking at vector equations in terms of R of t. So when we're trying to find a unit tangent vector, so in this case, unit tangent vectors are written as capital T of t. So that's going to be the unit tangent vector, and the formula for that is going to be the derivative of the vector equation, R prime of t, over the magnitude of R prime of t. And the reason we're doing R prime is because we're finding the unit tangent vector, since the derivative means the tangent. And notice it is very similar to the standard unit vector form. So for number 1, let's go ahead and find the unit tangent vector, capital T of t, of the vector equation R of t equals 6t to the 5th, comma 4t cubed, comma 2t, at the given value of t equals 1. So remember that the unit tangent vector, the formula for that, is going to be equal to R prime of t over the magnitude of R prime of t. So let's go ahead and find R prime of t. So R prime is going to equal, in a component form, the derivative of 6t to the 5th, start with that, is going to be 30t to the 4th, comma the derivative of 4t cubed, which is 12t squared, comma the derivative of 2t, which is simply just 2. Now we need to find R prime of t at the given value of t equals 1. So we can just plug in 1 for t. So R prime of 1 is going to equal, in component form, 30, comma 12, comma 2. Now let's go ahead and find the magnitude of R prime of t. Now we've already found R prime at the given value t equals 1. So now what we have to do is find the magnitude. So all we have to do is take the square root of the x component squared, so 30 squared is 900, plus the y component squared, 144, plus the z component squared, which is 4. So that will give us a value of the square root of 1048. And so you can also simplify this into 2 times the square root of 262, since 4 times 262 gives you 1048. So now let's go ahead and plug it into the formula of the unit tangent vector. So the unit tangent vector is going to be equal to the vector of R prime of t at the given t value of 1, which we found to be 30, 12, and 2 in this component form. So 30, 12, and 2, divided by the magnitude of R prime of 1, which we found to be 2 times the square root of 262. So 2 times the square root of 262. And now we can go ahead and simplify. So we just divide each component by 2 over the square root, or 2 times the square root of 262. So we'll get 30 over 2, which is 15, over the square root of 262, comma 6 over the square root of 262, and then comma just simply 1 over the square root of 262. And so that's the final answer for the unit tangent vector. So for number 2, let's go ahead and find the unit tangent vector for R of t equals cosine ti plus 3tj plus 2 sine 2tk at the given t value of 0. So once again, the unit tangent vector formula is going to be equal to R prime of t over the magnitude of R prime of t. So let's go ahead and find R prime. So R prime of t is going to be equal to, now the derivative of cosine of t is going to be negative sine of t, so negative sine of t times I, now plus the derivative of 3t, which is 3, times j, and then plus the derivative of 2 sine 2t. And so the derivative is going to be 4 cosine of 2t times k. And so now we need to find the derivative at the given value of t equals 0. So let's go ahead and find R prime of 0. So now the sine of 0 is obviously 0, so that's just going to be 0i. Now plus 3 times j, and then plus, now cosine, well 2 times 0 is 0, cosine of 0 is 1, and 1 times 4 gives us 4k. So that will lead us with 3j plus 4k. And so that is going to be the R prime of t. So we get 3j plus 4k on the numerator. Now let's go ahead and find the magnitude of R prime. So once again, we're going to take the square root of the x component, so the magnitude of r prime is going to be equal to the square root of the x component. Now the x component, there is no I, notice, so that's going to be 0. 0 squared is 0, plus the y component, so in front of j we have 3, so 3 squared is 9, and then plus the z component, 4 squared is 16. So we'll get the square root of 16 plus 9, 25, and so that will give us a magnitude of 5. So that will be our magnitude of r prime of t. Now to simplify, we can go ahead and divide the 5 to each of the components. So our final answer is going to be 3 over 5j plus 4 over 5k as the unit tangent vector. So now moving on to the next topic. When talking about parametric equations for vectors, we have to write in terms of x, y, and z when in 3 dimensions. So we have an x equation in terms of t, a y equation in terms of t, and a z equation in terms of t. So in order to write these parametric equations, once again, we must have a vector which can have the components a, comma b, comma c, and then we must have r naught. And so that is going to be that point of intersection or a given point. So that will just be x naught, y naught, and z naught. So the x equation is going to be equal to x naught plus a times t. The y equation is y naught plus b times t. And the z equation is going to be equal to z naught plus c times t. So for number 1, let's go ahead and find out parametric equations for the tangent line of the curve with the given parametric equations at the specified point. So the equations that are given to us is x equals t to the 5th, y equals t to the 4th, and z equals t cubed. And the specified point is at 1, 1, 1. So notice it asks for the tangent line, so we know we must take the derivative. Well, how can we write a vector equation for this? Well, r of t, the vector equation, in component form, we need to have the x component, which is t to the 5th, comma the y component, which is t to the 4th, comma the z component, which is t cubed. So now we can go ahead and find r prime to find that tangent line. So r prime of t is going to equal, in component form, 5t to the 4th, comma 4t cubed, comma 3t squared. So now looking back at the original parametric equations here, we need to find at what t value do we get the x value of 1, the y value of 1, and also the z value of 1. So what value can we plug in for t to get 1, 1, 1? And the simple answer is obviously just 1, because if we plug in 1 for a t here, we'll just get 1, so that will be our x coordinate. If we plug in 1 for y, we'll also get 1, which is our y coordinate, and then 1 for z, we'll also get our z coordinate there. So that means we're looking for the parametric equations for the tangent line specifically at the value t equals 1. So if we go ahead and plug in 1 here for t, so r prime of 1 is going to equal, in component form, 5, comma 4, comma 3. So that is going to be the tangent line at the specific value of 1. So this will be our vector that represents its components a, b, and c. Now r naught at the given point is obviously just 1, 1, 1. So in component form, that would just be, once again, 1, 1, 1. So that will be our x naught, y naught, and z naught. So once again, in order to write these parametric equations, so the first one, x, is going to equal x naught, which is 1, plus a times t, so a is 5, so we get 5t. Now y is going to equal y naught, which is also 1, plus b times t, so that would be 4t. And then z is going to equal z naught, which is also 1, plus c times t, so that would be 3t. So those are going to be the parametric equations. So now for number 2, we have x equals e to the negative t cosine t, y equals e to the negative t sine of t, and z equals e to the negative t. So let's go ahead and find the r of t equation, or the vector equation for this. Now the vector equation is going to have the x component, which is e to the negative t cosine of t, comma the y component, e to the negative t sine of t, comma the z component, e to the negative t. Now since we're trying to find the tangent line, we must take the derivative. So r prime is going to equal, now in this case we do have to use the product rule, so derivative of e to the negative t times cosine of t is going to be negative e to the negative t cosine t plus negative sine t times e to the negative t. Now the derivative of e to the negative t times sine of t is going to be negative e to the negative t times sine of t plus cosine t times e to the negative t. And then the derivative of e to the negative t is simply just negative e to the negative t. So now looking back at the original parametric equations, we need to find at what t value can we plug in for each the x and the y and the z equation to get an x value of 1, a y value of 0, and a z value of also 1. So now if you think about it, let's say we plug in 0 for t into the x equation. E to the 0 is 1 and cosine of 0 is 1, and we do get 1 for x value. If we plug in 0 into the y equation, sine of 0 is 0, so that's going to be 0. And then if we plug in 0 to the z equation, e to the negative 0 or e to the 0 is going to be 1. So we're looking for the derivative or the tangent line exactly at t equals 0. So we need to find r prime of 0. So when we plug in 0, now e to the 0 is going to be 1 times negative 1, so that will be negative 1. And then cosine of 0 is also 1, so we'll get negative 1 and then plus. If we plug in 0 here, sine of 0 is 0, so that's automatically going to make it 0. Now, when I plug in 0 into negative e to the negative t sine of t, sine of 0 is 0, so we get 0. And then plus, now cosine of 0 is 0, cosine of 0 is 1, and then e to the 0 is also 1, so we get 1 times 1 or 1. Now, comma, we plug in 0 here, e to the 0 is also 1 times negative 1, which will give us negative 1. So we'll get, in component form, negative 1, 1, negative 1. So that will be our vector equation with components a, b, and c. Now once again, r sub naught is going to be that given point that we had, which is obviously 1, 0, 1. So we can just rewrite it in component form as 1, 0, 1. And so r naught will contain x naught, y naught, and z naught. And so let's go ahead and write the parametric equation. So x, once again, is going to equal x sub naught, which is 1, plus a times t, which is negative 1, so we can rewrite it as 1. Instead of plus, we have minus 1 times t. Y is going to equal y sub naught, which is 0, so that we just leave it like that. And then plus b times t, so 1 times t is just t. And then z is going to equal z naught, which is 1. And then it's going to have plus c times t. So in this case, minus, once again, t. So those are going to be the parametric equations. Now, before I move on to the next set of questions, similar to derivatives, now let's say we're going to take the integral of the vector function r of t dt. Now, once again, it's the exact same process like derivatives. We're going to take the integral of each individual function inside of the vector. So, in this case, we're going to take the integral of f of t dt, comma, the integral of g of t dt, and then comma, obviously the integral of h of t dt. So for number 1, let's go ahead and evaluate the integral from 0 to 1 of 16t to the third power I minus 9t squared j plus 25t to the fourth k dt. So once again, when we take the integral of a vector function, we must take the integral of each individual component. So let's go ahead and start with taking the integral of 16t cubed. So the integral from 0 to 1 of 16t cubed dt is going to be equal to, now we take 16t to the fourth over 4, so we're left with 4t to the fourth. And we're going to evaluate from 0 to 1. So when I plug in 1, we'll just get 4, and then minus when I plug in 0, we'll get 0. So we're left with 4. So we're left with 4i as our x component. So now let's go ahead and take the integral of 9t squared for our y component. So the integral from 0 to 1 of 9t squared dt is going to be 9t cubed over 3. So we'll get 3t to the third power. Now, same process, we're going to evaluate from 0 to 1. So we'll get 3 minus, when I plug in 0, we'll get 0. So we're left with 3. So notice there's a minus here. So we're going to have minus 3j. Then let's go ahead and evaluate 25t to the fourth. So the integral from 0 to 1 of 25t to the fourth dt is going to be 25t to the fifth over 5. So we're left with 5t to the 5th. When we evaluate from 0 to 1, it's the same process once again, so we get 5 minus 0, so that we're left with 5. Since there's a plus here, we can put plus 5k. So that is going to be the integral. So now for number 2, let's evaluate the integral of e to the t times I plus 2t times j plus natural log of t times k dt. So once again, we have to take the integral of each individual function inside the vector. Now the integral of e to the t dt is obviously still just going to be e to the t. So we're going to write e to the t as our x component times I. Now for the integral of 2t, the integral of 2t is going to be t squared. So we have a plus t squared j. And then finally we have the integral of the natural log of t. And so the integral of natural log of t is simply, if you memorized it, it's going to be, and so finally we have the integral of the natural log of t. And so the integral of ln of t, now you could use integration by parts, but it's easier to actually memorize the integral. And so the integral is going to be t times the natural log of t minus t. So we can put t times the natural log of t minus t, and remember that entire thing is with the k unit vector. So we have to put the entire thing in parentheses multiplied by k. Now remember, this is going to be an indefinite integral, so we have to have the plus c at the end. So that is going to be the final answer.